Okay, so we were talking about, last time we met, we were talking about graphing quadratic functions in vertex form, right? So, and here's a quick reminder what we mean by that. Vertex form of a quadratic function or equation is where we've got f of x equals, and then we've got this template for our quadratic function, right? This is really just the x squared parent function where we've added the values of a, h, and k. Remember, a, which is the vertical dilation factor, that's always what we're multiplying in front of the x squared function. H is what we're subtracting from x inside the x squared function, right? And that represents the x coordinate of the vertex. And k is the number that's being added outside of the x squared function, and that's the y coordinate of the vertex. And then we also know that the axis of symmetry of the function is just the vertical line x equals h. Okay, so we're going to take it from there. Just stare at that stuff for a second and jog your memory. Okay, so we did this example where we graphed this function, right? And how did we do it? Well, we said that h was -1, so that's the x coordinate of the vertex. K is -2, so there's our vertex with coordinates -1, -2. That's our starting point, right? And then we saw that a was -1/2, and so we, starting with our vertex at -1, -2, we've got to create the shape of a parabola that matches that value of a, right? So instead of normally for our parent graph, we would go over 1 and up how far on our parent graph? If we start at the vertex and we go 1 to the right, how far up would we normally go? Type it in chat, please, everybody. Okay, good. Everybody type it in chat. I'm not seeing any responses. So starting at the vertex, if I go 1 to the right, I go up. What? Are you guys typing stuff and I'm just not seeing it? Oh, there we go. Okay, no, that's not what I'm looking for. Let me be more specific. So if we start at the vertex, right? I don't want coordinates here, but I just want to know, like, if an ant were to walk 1 to the right on that regular x squared parent graph, right, a regular parabola, how far up would it go when it goes 1 to the right? And the correct answer is 1. There you go. 1 is what I'm looking for, right? Because it would go over 1 to the right and up 1 squared, which is 1. What if the ant were to walk 2 to the right from the vertex on our x squared graph, our regular shape, or just our plain vanilla shape? How far up would it go if it went 2 to the right? So we could say, what would the height of the function be if I went 2 to the right? Yeah, good. It's 2 squared, which would be 4, right? Okay. One more. What if the ant went 3 to the right on our regular x squared graph? How far up would I go? Okay, good. 9, up 3 squared. Very good. Okay. So then we're going to take these regular heights, these regular vertical distances that we're talking about, right? And we're going to multiply all of those by a. That's the job of a, to get our transformed function, our dilated function, right? So instead of going over 1 and up 1, we now would go over 1 and up 1 times a, up 1 times -1/2. Well, that's -1/2. So I'd go over 1 and down 1/2, right? Instead of going over 2 and up 4, I'm going to go over 2 and up 4 times -1/2, which is -2. So over 2 and up -2 is down 2, right? And then all I'd have to do is just reflect those points over my axis of symmetry, the vertical line through the vertex, to get some points on the other side for free that I could just connect in a parabolic shape, okay? That works, right? That's an easy way to do it. That's the best and easiest way to graph parabolas. Okay? There is another way, though, that always works that I want to remind you of. Not that you should necessarily do it this way, but if you ever forget, or you're just, you forgot how to, or it's a different function maybe, right? You can graph any function using this trick I'm going to remind you about now. And it's not much of a trick, it's just a t-table. Right? So if we just make a t-table where we've got a column for x input values and a column for y output values, well then I can take any value I want. Like we already knew that the vertex had coordinates. You guys already told me this last time, that the vertex had coordinates -1, +2, right? Well, I could find that out. I could prove that by plugging -1 into my function in a t-table also, right? If I plug -1 into my function up here, what do I get? Well, f of -1 would equal, what do I get when I plug -1 in there? I get -1/2 times -1 plus 1 is 0 squared is just 0. So -1/2 times 0 minus 2. Well, that's just 0 minus 2. It gives me an output of -2. And what do you know? Those are the coordinates of that point, right? We already knew that. So that one I already knew, but I could plug in some other ones too, right? Like I could plug in the value. What if I want to go 1 to the right of that? So I start with an x value of -1. Now let's plug in 0. I could just calculate f of 0, right? -1/2 times 0 plus 1 is 1. 1 squared is 1. So -1/2 times 1 minus 2, wasn't that just -2.5? We'll just make it a decimal. And what do you know? Those are the coordinates of that point, aren't they? Right? 0, -2.5. From the origin, I don't go anywhere horizontally. I'm just going down 2.5. Yeah, it works. If I pick the point 1, f of 1 would be -1/2 times 1 plus 1 is 2, squared would be 4, minus 2. So that's just going to give me -2 minus 2 is -4, right? Well, what do you know? Those are the coordinates of that point right there. So I could just create a t-table to generate these points also, right? I think that's a little bit harder and more time consuming to do though, personally, okay? All right. Okay, now we're going to go backwards. Okay, this time instead of being given a function and we have to graph the function, they're giving us the graph and we have to write the function. Okay, so what do we know about the function? Well, we know this is what it needs to look like, right? It needs to look like the vertex form of a quadratic equation, right? Or a quadratic function. So that's the result we're trying to come up with. We just need to know what values are we going to plug in, what numbers are we going to plug in for A, H, and K that correspond to this graph. But that's always where we start, is with this blank template. And what is this? I mean, once again, this is just our parent function, x squared, where we've sort of preloaded the A and the H and the K. And all we have to do is plug in the values now, right? Okay, so you tell me, type in chat, what are the values of H and K? Type it in chat. What are the values of H and K for that parabola that's graphed there? Got 5 answers. I need more. Everybody answer here. If you're not 100% sure, that's all right. Give me your best guess. Okay, there's still some names I haven't seen on there yet. Show me you're here, please. Give me an answer. I'll even take a question mark, but I want to know you're here. Okay, let's go back to this page for a second. What's this tell us here? It tells us that H and K are the coordinates of the vertex, right? So people were on the right track, but I got some answers of 2, 3, and some answers of negative 2, 3. Which one should it be? Negative 2, 3 or positive 2, 3? Should be negative, shouldn't it? Right? Because H and K are the coordinates of the vertex, and the coordinates of the vertex are negative 2 and 3, right? So this is HK right there, isn't it? Right, so we know we're going to be plugging a negative 2 in for H and a positive 3 in for K, aren't we? The only thing that remains to be seen now is what is the value of A? And this is probably the trickier. The H and K are pretty simple. You just look at the coordinates of the vertex, right? What about A, though? So here's our vertex. We can see there's the vertex, right? There's our vertex. Here's another convenient point that crosses, at a corner of the graph paper. Here's another one right there, it looks like. Okay. So let's think about this graph here, this blue graph. When we start at the vertex, when we go 1 to the right, we're going up by negative 1. Okay, we just have to compare that to what we normally would do. What would we normally do for our parent graph? If I went 1 to the right, I go up by how much? Everybody? Good. I'd go up 1, wouldn't I? So normally we'd expect to go over 1 and up 1 to get a point right there, right? Because our normal parabola would do something like that, wouldn't it? Okay. Well, if I want to know what A is, I just have to figure out what did I multiply my normal height by to get my dilated height. So this is the equation kind of that we can always use, the formula. I want you to see why we do this though too. So the formula would be what we might call our parent height, because this is our parent function, right? There's our parent function. It has the shape y equals x squared. So we'd multiply one of our parent heights times A should equal our dilated height. So what did we end up with? What does the graph actually look like? So in this case, we'd have the equation 1 times A equals negative 1, right? Our regular parent height times A equals negative 1. Well, 1 times A, isn't that just A, right? So we end up with A equals negative 1. How else could we do that? Well, we could use this point down here also, right? What about this one? In this case, we would be going 2 to the right and up by negative 4. Okay, normally we would expect on our parent graph to go 2 to the right and up how far? Type it in chat. On our regular parent graph, y equals x squared. If we go 2 to the right, we go up how far? Quickly, type that in. Good, I'd normally go up 4. Good. Okay, so normally I'd expect to go up 4, but I'm actually going up negative 4. So we could make an equation out of that. Our normal parent height should have been 4 times A equals our dilated height, in this case, is negative 4. Okay, so what would I do here to solve for A. I mean, just think about this as a simple algebra equation like 4x equals -4. How do I undo multiplying A by 4? What do I do to both sides? Type it in chat. Good. Divide by what? Divide by 4. Okay, good. Divide each side through by 4 to solve for A. And what do you know? We get the same answer. We have to. -4/4 is -1. Either way, I get -1 for A, right? So though we know what the numbers are that we're plugging in then for this blue graph, we're plugging in an A value of -1, an H value of -2, and a K value of 3. Those three parameters are the values that give us this parabola. Think about those like dials on a machine, right? If I'm dialing in values for A, H, and K, I'm just tweaking my parent graph to turn it into this graph instead, right? Okay, so let's simplify that then. What does that give us? If I want to rewrite this, plugging those values in, -1 goes in for A, so I would just write that as a negative in front of my x squared function. I'm going to subtract a -2, so x minus -2 becomes an x plus 2 inside my x squared graph. And then finally, I'm adding a value of 3 when I plug 3 in for K. So there it is. There's my function. Okay, everybody give me 1 to 5. Okay, good. Numbers are climbing. That's good. Let's do another one. One more. A little harder one. Okay, what about this guy here? So they give us a graph, right? And we've got to figure out what values to plug in for A, H, and K for that parabola that's graphed. Okay. All right, well, one thing we could do here, this is a little bit strange. Look, they give us our vertex and they give us a point on the left of the vertex. We're used to seeing points on the right of the vertex, right? So I'm gonna draw our axis of symmetry in here. How about? There's the axis of symmetry that goes through the vertex and splits this thing into two equal halves. The equation of that, if I want to write it down, the equation of that is x equals 4, right? There's our vertex. Well, look what we can do here. We know that we have this folding or reflective symmetry. So if I've got a point over here, I could just reflect that over to the other side to create like a partner point over there, right? So let's use these two instead, how about, right? They're on the right side. We're more used to working on the right side. So let's think about that. Well, first of all, what are the values of H and K? You guys can all tell me that right away. What value am I plugging in for H? Everybody tell me. Type it in chat. What value goes in for H? Okay, good. 4, right? Because that's the x coordinate of the vertex. Good. So we know right off the bat, we've got H is 4. What's K? Type that in. Okay, good. -2. All right. Okay, easy stuff. We got those. But what about A, though? We got to figure out A. So let's pick 2 points that are convenient. There's 2 convenient points right now. What's going on with these 2? So it looks like we're going over by how much? 1, 2, 3, 4. And I'm going up by 2. Okay, how much would I normally expect to go up? If I go over by 4 on my regular graph, my parent graph, what should my parent height be when I go over by 4? The height of the parent graph there. How far up would I need to go? Type it in, please. Yeah, 16, right? 4 squared. Good. So I'd go over 4 normally, and I would go up a total of 16, right? Okay, so then we should be able to figure out what A is. I took my normal height of 16 and I multiply by A to get my dilated height, my squashed height of only 2. Okay. Everybody give me a 1 to 5 on that. Do you see how we set that up? Give me a 1 to 5 on that. Okay. Everybody, type it in if you're not showing me fingers. Okay, good. And remember, where's that coming from? It's just this parent height times the dilation factor gives us our stretched or compressed height, our dilated height, right? Okay, so then all I've got to do is solve for A. Well, how do I undo multiplying by 16 to get the A by itself? What do I do to both sides? Type it in chat. I got to figure out what A is. Okay, good. Everybody agree? We're going to divide both sides by 16 to solve for A, to get that A by itself so we can figure out what its value is. So we end up with A equals 2 over 16, which I could reduce that fraction to 1/8. And so now all I've got to do is plug those numbers in and I'm done. That's my function. Whoops. So we end up with f of x equals 1/8 times the quantity, right? Because the 1/8 is in front of my x squared function. I'm subtracting 4 from x inside my x squared function, and I'm adding -2 or subtracting 2 outside the function. There it is. That's kind of a tough one, but even that one we can do it. No big deal. The hard part probably, not so hard, but it just takes a little practice. The part that takes the most thinking is determining what A is. And once again, all we're doing is we're picking for a given distance from the vertex. How far for a given, like in this case, we're moving 4 to the right from the vertex. So when we move 4 to the right from the vertex, we're just comparing what we normally would expect from our parent function to what we actually got with our squashed function. Okay? All right. So what about one like this then? This is a little bit different, right? This guy, there we go. Okay, I'm throwing something at you here. It's not really that important, but I just want you to see, what if we have an inequality instead of an equation? Don't let that part bog you down, though. The fact that this is an inequality really doesn't change much, okay? The main part of this is still just graphing the parabola. Let's think about what this might look like, though. We dealt with graphing linear inequalities, inequalities that were lines, a while ago. And what would we say about that, right? If we had something like f of x is less than mx plus b, if it's a line, well, then we had a boundary line. We had to graph the boundary line. And if it was f of x is less than the boundary line, did we shade above or below our boundary line? Type it in chat. Yeah, good. We just shaded below, didn't we? So what's the difference here? It's the same concept, only this time, instead of shading below a boundary line, we're going to shade below a boundary parabola. It's just not a line. It's just a different shape that's forming the boundary, right? Okay, so let's deal with the shape of the boundary first. What are the values of h and k for this function? Type them in chat, please, everybody. What are the values of h and k for f of x? Okay, pretty good. Now the one question is h 3 or -3? Everybody's right that k is 0 because there's nothing being added outside. What's the value of h here? And this is the one that I realize this one gets a little confusing working with these h's. Is it 3 or -3? Well, if we look back real quick at our standard form, where's one that's easier to see? Right there, right? Our standard form. H is always the number that is being subtracted from x, right? So in this case right here, it's positive 3, right? It's always going to be the opposite of whatever that symbol is between the x and the number, okay? So it's positive 3, right? And doesn't that make sense? I know there's a lot of, your brain's trying to organize all this information here, right? But this makes sense even if we think back to when we talked about transformations. Didn't we say that subtracting a number from x meant we moved it to the right? Yeah. And what does that mean? The vertex is going to end up with a positive x coordinate then, right? If it gets moved to the right. So our vertex is at 3, 0. Let's take care of that. So I can slide this guy to the right to there. There's our new vertex, right? Okay, now what? What's the value of A? Type that in. Okay, good. It's -1. Okay, so then we should expect that here are our normal parent graph values, right? There's our vertex. We go over 1, we go up 1, we go over 2, we go up 4, right? We go over 3, we go up 9. Okay. If A is equal to -1, we're going to multiply those normal heights. So there's 1. We're going to multiply those normal heights by -1. So now we'll go over 1 and we'll go up -1. We'll go over 2 and we'll go, instead of going up 4, we're going to go up 4 times -1. So we'll go up by -4, right? So where are we going to end up getting our points? Well, we got our vertex. We already know, right? That's not changing. Vertex is our starting point. That one stays put. Come on. There we go. We've got a point here. We've got a point here. And we keep on going. And then I could reflect all of those over my axis of symmetry. Right, there's my axis of symmetry. And so I could reflect those guys over the axis of symmetry. So that one, instead of being 1 to the right, it's got to be 1 to the left of that axis. Instead of being 2 to the right, this one has to be 2 to the left. So I get points there and there, right? Now all I have to do is just connect those and make a parabola, right? This is going to be tough for an artistically challenged person like me. There's my boundary, right? Doesn't look so great, but you get the idea. Okay, well, let's go back up to the original inequality here. So notice I'm not including an equal sign in my inequality. So what's that tell me about my boundary that I'm drawing? Think back to what we did with lines. What did we say about a boundary line if the inequality didn't include an equals? Okay. Yeah, it was dashed, wasn't it? Okay, so we got to make a dashed line then. Well, here's my way of making a dashed line. I'm just going to use my eraser, and I'm going to just erase some little pieces of this thing, huh? Right, so there's our dashed boundary line. And then you guys already told me that if I have f of x is less than, that means that I'm shading below, right? So we end up with then something like right? And it just goes down forever, right? That parabola. Okay? Give me 1 to 5. Does that make sense? Okay. And really, the important part here is not the inequality part. The part I'm most concerned about is, can you graph the parabola, right? That's the main thing. It's just sort of a little added bonus that we get to see in inequality. I'll tell you what, I'm going to graph, just so we get a little better picture than my crappy drawing, I'm going to graph this in Desmos real quick and take a picture for the notes. Something that'll look a little better. So we've got, when I do an inequality, remember I can't use f of x, I have to use y in Desmos for some reason. So y is less than, but I can use y, same as f of x. Y is less than negative the quantity x minus 3 quantity squared. Oops, squared. Okay, and so it matches our picture. Let's make that blue, how about? There we go. So for your notes, there's what it ends up looking like. All right. What about this one? Let's do one more of these. Okay, what about the values of h and k for this guy? Type them in chat for me. Values of h and k. Everybody, type that in. It's our last example. I'll let you work. Okay, good. -1, -7. I like it. So we know then that our vertex is going to get dragged over to the point -1, -7. So right there. Okay. And what about the value of a? What's a in this case? Type that in. Okay, good. All right, it's 4. So I'm multiplying my normal heights by 4 here. Okay, so now I want you to fill in the blank for me in chat here. So now, when I go 1 to the right, when I dilate this function, starting at the vertex, when I move 1 to the right, I move up how far? Fill in the blank. If a is equal to 4, when I go 1 to the right, I should move up how far? Okay, I like it. Good, right? I'm moving up by 4, and the reason for that is that my normal height of 1 I'm multiplying times a to get my answer, right? Wasn't that just 1 times 4? Gives me 4. Yeah. So I should expect instead to go over 1 and up 1, 2, 3, 4. So right to there, right? And there's going to be a point. Okay, same question. Same question, only now fill in this one for me. If I go 2, right, I go up how many? On my stretched graph, how far up should I go? Okay, I'm going to tell you the answer is not 8. Ah, okay. How far would I normally go up? I mean, how far would I go up when I multiply by A? Let me ask you this. How far would I normally go up? If I go 2 to the right, how much would I normally go up? I'd normally go up 4. Right, good. Okay, so I'd normally do this, right? I'd go over 2 and up 4. But if A is equal to 4, right, then I'm going to multiply my normal height by 4 to get 16. Good. Okay, so that's my answer. I'm going to get 16. And once again, what's the reason? Because my normal height of 4 times A, which is 4, oops, that's supposed to be blue, equals, I just want to keep my colors consistent. I'm kind of particular about that. Right, so A is 4. If I multiply my normal height by A, which is 4, I get my stretched height of 16. Okay, so now I should go over 4 and up 4, 8, 12, 16 right there. Okay, and so look, I've got these 3 points on my purple graph. I've got the vertex and I've got those two. Let's go ahead and graph in real quick. We'll graph our axis of symmetry again so we can reflect those. Oops. There's my axis of symmetry, so I can reflect him over to that side, him over to that side, and I get points there and there, right? And now I've got enough to make my parabola. There it is. Okay. And let's see, if I go back to my original inequality, look, this time I'm actually including an equal sign, right? So it's a solid boundary. If I've got f of x is greater than or equal to my boundary, doesn't that mean that I'm shading above the boundary, right? And so my final picture should look like this. Right, I'm shading everything above that boundary. Okay, good? Makes sense? If I put that one in Desmos to get a little prettier picture, y is greater than or equal to 4 times x plus 1 squared minus 7. Okay, there it is. Better make it purple so it matches our picture. It's important, right? And there we go, right? There's our picture. Okay, I'll even do Let me even do this. Put in a couple points here. So we'll put in the points. -1, -7. Zero, -3. And what did we say it was? If I go up 16, so 1, 9. There's a good picture. Okay, you can work. You got a little time here at least. How much time did I give you? 7 minutes? Maybe you can get a problem or two done. Ask some questions if you need to. I'm going to go ahead and I'll put the notes in the video up right now so you'll have these available too.